Hi everyone, my name is Ermis, and today I'll present our work on machine learning part course allocation. This is joint work with Behnoosh, Zamanlooy, Jakob, Weissteiner, and Sven. Seuken. The combinatorial assignment problem arises in large educational institutions every semester when they have to assign courses to their students. There's a limited number of seats available in every course. Students can have combinatorial preference over them, and monetary transactions are prohibited for fairness reasons. These factors combined make this an instance of the combinatorial assignment problem. The dimensions of interest are the usual suspects, namely efficiency, fairness, and good incentives. Our goal is a practical mechanism good in all of the dimensions. The state-of-the-art mechanism for the problem is cost match. It is a practical implementation of the approximate competitive equilibrium from equal incomes mechanism by Ermis. Intuitively, it's good in all three dimensions of interest by making slight compromises in each one. It was first introduced in Britain, since been adopted in many top educational institutions. Let's start with an overview of the mechanism. First, students report their preference to the mechanism using a specifically designed graphical user interface. There's a drop-down list of all courses. Students can select any course they're interested in and input a number between 0 and 100. That's called the base value. Additionally, they can select any pair of course they want and input a number between -100 and +100 for the pair. That's some extra utility, positive or negative, associated for taking both of those courses at the same time. A student's utility for a schedule is taken to be the sum of base values and adjustments for course contains. Now let's start with the work of the mechanism. The idea is that a well-raised equilibrium would have many nice properties for this problem. It's efficient, it's Pareto optimal, and if students have the same budget, it would also be integrated. But there's a tiny detail missing that this thing most likely does not exist. However, Eric Wood has proved that an approximate version of it, where the student budgets are almost equal, and the budget does not exactly clear, but only approximately clears, always exists, and maintains approximately those nice properties. Specifically, students achieve very close to the fair share of the allocation. Additionally, the mechanism has entry bound by a single rule, meaning that if student A is jealous of the assignment of some student B, I can remove just a single schedule from student B's assignment and the entry goes away. And in large markets, the mechanism strategy. Stages 2 and 3 just ensure that the stage 1 allocation is feasible. In practice, they're not usable. Prior to the adoption of course match by Gordon, significant lab experiments were conducted by Ermis. In those experiments, they found out that students were happy with course match compared to the previously used mechanism in school, the bidding points option, and that they perceived the mechanism as more fair. They concluded that students were able to use the mechanism well enough to realize its theoretical benefits. At the same time, they uncovered some shortcomings of the mechanism, especially related to its reporting limits. Students on average, only reported a base value for half of the cost of the experiment, and they only reported one adjustment out of the 300 cost. The language itself also has limited expressiveness, as it can capture at most pairwise interactions among courses. These factors combined led to students making reporting mistakes, which helped the mechanism's efficiency. And this should not come as a surprise. It's often the case in market design that one of the key challenges is getting the agent's preference out of their heads and into some well-functioning theory mechanism. And this is where we come into play. Our idea is to use machine learning to improve preference elicitation by focusing the student's attention into the most useful part of the allocation space. Now I compare our mechanism against the original one. Students report their preference using the same graphical user interface that they're already used to. Afterwards, we initialize a machine learning model for each student based on the graphical user interface reports. This model takes us into the full course schedules and outputs a student's predicted utility for the schedule that was given as input. Using those models, we estimate approximate clearing prices for the mechanism that we can use to ask more informative queries to the students in the next phase. In this phase, we iteratively ask the students' queries to fine-tune their models. Those are completely optional for each student, and each student can answer as many or as little of those as they want, including none. With the upshot being that the more they answer, the more this will benefit them in the last phase, where we compute a final allocation based on all models of those students. And what type of queries do we ask? We ask very simple comparison queries. Do you prefer Schedule A or Schedule B? Comparison queries are cognitively a lot simpler for students to answer. They have been treated as ground truth in prior works for these exact problems. With our approach, they are generated instantly for each student. And importantly, unlike options where people need to synchronize the reports, each student can answer them asynchronously. Now, what's our learning algorithm for learning on those two very different types of reports? The idea is that for the graphical user interface reports, we construct a data set of schedules, implied value pairs based on those reports, and then we can train using simple regression rules. For the comparison queries, we adopt the Bradley-Terry model that says that the probability of a schedule X being better than schedule X prime is equal to the sigmoid of their value difference. And this allows us to treat this as a classification problem. A final technical detail, the graphical user interface reports are a lot less accurate compared to the cognitive user comparison queries. So we use a much higher regularization for it. And the other technical part is how to generate comparison queries. For this, we have to create our own algorithm, which we name online binary insertions. The idea is that for each student, we maintain a complete ordering of already queried schedules. Let's say that for some students, the list looks like this at some point. In the parentheses above, we show the students' true values for those schedules. Then we quote unquote ask the machine learning model what its prediction is for the student's most favored schedule that's not already on that list. And then we just ask comparison queries trying to insert that schedule into that list. So we'll ask the student, which schedule do you prefer among S5 and S2? In this case, the student will say, I prefer S5, and then we'll compare against S4. The student will say, I prefer S4, and the list will look like this. If you want an intuition of why this algorithm is a good idea, it guarantees a superlinear amount of ordinal information. Let's say at some point the list has a length of n. Then by asking log n queries, we can insert one more element into it, and we get n pieces of ordinal information back. And actually, this is just a worst case scenario. But if we test the empirical performance of different algorithms with respect to this objective, it outperforms everything else we tested by quite a significant margin. The green line is the random algorithm, but just takes two schedules at random each time. And the orange line is an naive algorithm that always compares against what was the previously first discovered schedule. Additionally, now we plot in the y-axis how often the network's prediction for what the student's answer to a comparison will be right before the student actually answering that comparison question. For the other two algorithms, after a student has answered just 4 comparison queries, the machine learning model can correctly identify the answer in over 90% of the cases. While for this algorithm, throughout the process, the network average hovers at around the 50% mark. Intuitively, those comparison queries are more surprising for the network, which means that they are more informative. Formally, we can prove that on expectation, they lead to the largest change in the machine learning model's weight. Now we move to experiments. For our experiments, we have to use a simulator. Why? For one, we need many instances so that we can compare different approaches and establish statistical significance. And two, even if a couple of publicly available instances of the problem exist, they only relate to how the students report their preference to the mechanism. We have no data on what the true preferences are. We use simulated instances. Each instance has 100 students and 25 courses, just like in the lab experiments of Budis and Kessler. And we tuned the students' reports to match all statistics of that experiment within at most 3%. The simulator that we used for our experiments is already publicly available. I think this may be of interest to some of you, and very soon we will also publish the rest of the book. Now let's start with our experiments. In the x-axis, we plot the number of comparison queries that the student answered in course months. In the y-axis, we plot the average student utility. In the most realistic scenario, with students answering just 10 comparison queries, we're able to improve average student utility by over 10 percentage points. Just to put this number into perspective, if we compare course notes, this, which is considered a state-of-the-art mechanism, to random serial dictatorship, that difference is only 3.6%. As the number of comparison queries increases, our results improve further. In terms of minimum student utility, our performance gains are even more substantial. With just 10 comparison queries, we improve minimum student utility by over 25 percentage points. Suppose our mechanism gets implemented in practice, and a student is considering opting in and answering some comparison queries. A natural question is, how much would that student benefit as a function of the number of comparison queries that he has answered? We perform exactly this test by comparing her allocation if we were to use her cohort reports versus if we were to use her MLCM level report, holding every other student fixed. In all settings that we tested, the student would prefer the allocation under MLCM in at least 71.9% of cases, while she would prefer her allocation under course in at most 17.1% of the cases. In the rest of the cases, she gets exactly the same schedule under both mechanisms. And finally, her expected gain from opting into our mechanism and answering comparison queries is at least 9.6%. To put those results into perspective, the same exact experiment was performed in Wharton, comparing course to the previously used mechanism, the bidding points option. In that experiment, 42.4% of the students preferred course notes, 31.8% preferred the BPA, while the rest were neutral. And those results were considered good enough to actually switch from the bidding points option to course notes. Finally, we test the robustness of our mechanism to variations in the mistakes that the students make. To do this, we multiplied all parameters of our mistake simulator by a common constant. If that constant is larger than 1, students make more mistakes, while if it's smaller, the opposite is true. And throughout a very wide range of this parameter, our mechanism remains substantially better compared to course notes. If you want an intuition of why this is the case, when the students are more accurate in course notes, this also benefits us because we are also using those reports to initialize reports. Finally, many schools using the mechanism use a different reporting language. After acceptance of this paper, we adopted our mechanism to also work in this language. So these are exactly the same tests, and in this, we perform even better. Our performance gain is even larger. Finally, throughout this paper, we took great care in making our mechanism as easy to implement in practice as possible. It allows the completely asynchronous interaction of students with the mechanism. The participation in the machine learning component is completely optional for its student. Opting into the machine learning component is beneficial, even if there's just a single student doing so. Something that I didn't show, but our mechanism is computationally cheap. In fact, it's even cheaper than the original Cosmos. And finally, it is plug and play compatible with the existing Cosmos implementation. And those efforts have paid dividends as we're currently getting very close to actually filling this in practice. To conclude, we've introduced a novel way of listing preferences for a combinatorial assignment problem. We've improved efficiency in minimum student utility versus the state-of-the-art method of the problem. Our results are robust across a very wide range of settings and mistake profiles, and upgrading to MLCM is easy for universities and seamless for their students. That's all I have to say. Thank you. The full paper is available, and I'm getting in the job market soon, so that's all. Thank you very much.